Alrighty, ladies and gentlemen, and welcome back to the next edition of Chris Practice Code Jam. So let's get the next question up, and then we'll make it happen, Captain. Code Jam 2017. Yeah, it's just right there. Okay, problem C, bathroom stalls. I'll link this in Twitch chat over on my other monitor, so you don't have to see it. I've got to kick out a little early today, so this will probably be about 30 minutes long. Oh, excuse me, that's a burp that came through on the screen. So I'm not seeing my Twitch chat. I don't know why. I'm not seeing the messages I put up, so that's a little strange. But, whatever. Look at the chat. Right. Yeah, we'll see if that can come up. Not a problem. Okay, let's talk bathroom stalls, shall we? Let's pull that up. Okay, I am live, right? Let's make sure that's coming through. Yeah, I'm live. Great. Okay. Bathroom stalls. Oh, that's analysis. I don't want that. Okay. So, the actual question. Send that. Right. A bathroom has n plus 2 stalls in a single row. N stalls are for users. They try to choose a stall that is as far from other people as possible. To avoid confusion, they follow deterministic rules. Nice. LSS and RSS. With the farthest closest neighbors, that is, those best for which the minimum of LSS and RSS is maximal. If there's only one, they choose it. Otherwise, they choose the one among those where max LSS and RSS is maximal. Okay, so if the minimum is the same, they go to the further one, say which further one is far away. Makes sense. Sorry, eating some pork over here. It's delicious. K people are about to enter the bathroom. Each one will choose their stall before the next arrives. Nobody will ever leave. When the last person chooses their stall, what will the values of max L sub s and R sub s and min L sub s R sub s be? Case X, Y, and Z, where X is the test case number, Y is max L sub s, and Z is min L sub s. Just calculate. Okay, so for the large data set, ooh, we got a large number of stalls, right? Okay, so given an absurdly large number of stalls, a bunch of people are going to come in, and we need to find out how far the closest stall is, and how far the nearest stall is. Okay. I have not thought much about this one. In fact, this is really the first time I'm sitting down to think too much about it. So I'm learning things, right, about streaming. One of them is you should probably not eat lunch on stream because it makes it hard to program and talk. Okay, so here's what I'm thinking. We have this, essentially, set of stalls. And people are going to come in, and so the first one's largely going to go to the middle, right? That's going to return the number of stalls on the left and the number of stalls on the right. And the next person that comes in is going to say, okay, which of these two is bigger? Take the larger of those, and then it's the same problem on a smaller set, right? And the next person that comes in is going to say, okay, there's 3 gaps to choose from, essentially. Find the largest gap, run that same problem, now I got 4 gaps. Now, I don't necessarily yeah, so here's really where we're at, right? At the end of the day, what this boils down to is given some integer, or in this case, long, so given long L, of contiguous unoccupied stalls. Find out which stall within L they're going to go into, right? And then I'm going to return 2 longs, which are the new contiguous spots there, right? Huh. It's not too bad. Now, here's what I'm thinking of doing, and I know this won't quite work. Although, maybe it might. I mean, it's not guaranteed right now. So I'm going to start off with 1 long. Let's just say it's 1,000, right? Person comes in, I put them at slot 500. And that's going to return, the left side and the right side. So now I have essentially two blocks of size 500. I'm going to keep a map, okay? And it's going to be a map from long to integer, maybe. Okay? And the key is going to be the size of the contiguous chunk, and the int is going to be the count of that chunk. Because it's distinctly possible, because currently I've got like 2 contiguous chunks of size 500. So for everyone that comes in, I'm going to have to say, okie dokie, what is my largest contiguous chunk? And what size is going to add. Now, here's the problem. For the large test case, right, n is going to be extraordinarily large, 10 to the 18th, right? That's a big number. And I can't just iterate through one after the other, after the other, after the other. So, clearly I need to find a way to do this faster than that. So how am I going to do this faster than just putting them in, putting them in, putting them in, putting them in, right? It's a good question. Now I could just like do it the naive way and get the 2 small data sets out of the way. And then maybe the large data set will present itself with a better solution in the moment. Good question. Good question indeed. So we're really, honestly, we're just subdividing this thing a number of times. So I feel like if it was a good clean number, I could almost take the log base 2 of it, right? Because, really just dividing it into, breaking it down into segments is really all we're doing. So given, now of course if it's an ugly number, then we have to deal with like the boundaries, and that's kind of hairy. Alright, so here's what we know. Let's just pretend if it were nice and even, right? The first one cuts it in 2. The next one would make it into 3, and the next one 4. Now at that point we've got 4 more or less equally sized compartments, right? So the next 1, 2, 3, 4 all have the same answer, give or take, right? And there's definitely some rules we have to take into account there. So then we've got room for 8, 2, 3, 4, 5, 6, 7, 8. And then we'll have the next one. Should be able to put in 16 guys with the same answer. And then we should put in 32 guys with more or less the same answer. Now, once again, if we start with a weird number that's not easily divisible by 2, we'll have to handle that because one side will be 4, the other side will be 3, and it will be hairy. Now, of course, we can assume 1. So if we did 7 really quick, 1, 2, 3, 4, 5, 6, 5, 6, 7, right? So when the guy comes in, we put him right in the middle. So then we have 3 on the left and 3 on the right. So we're kind of breaking stuff up. So then we put one guy there, and then one guy there. Oh, see, now this is also interesting because, in that scenario, if there's like 7, we put guy in the middle, and then we put one more in, and max left, depending on where we did it, right? Well, I guess no, there are very deterministic rules. Man, I'm not seeing a good way to do this without like straight up putting them all in, like iteratively. But when you have to do something 10 to the 18th times, that's just not a good idea. So I don't know how we're going to do that yet. Now wait. Yes, I do. Yes, I do. We can do this, right? Yeah. Yeah, we can skip steps. We don't have to do all of them. Here's what we do know, right? Yeah. Okay. So let's take a look at the 7 case. And I'm sorry you can't see my paper that I'm writing on. You can't. I'm just drawing on my paper. So if we look at a set of 7, right? So we start with 7, which is a terrible base case. I don't know why I'm not starting with something good like 8. Let's start with 7. JK, we'll do 8. 1, 2, 3, 4, 5, 6, 7. So we draw 7 lines, which gives 8 slots. So one guy gets in. We want to have maximum distance away. Now here's what's funny about 8, is that it's not super duper good because you have to pick the left side. So we put one guy in index 0, 1, 2, 3. Yeah. So his max L at this point is 1, 2, 3. There's 3 holes between him and the next guy, and max R is 4. So you have 3 and 4 on the first guy. And then we have a scenario where we put the second guy in. Now, we need to pick a location that will give him max L and max R. In this case, that's going to be index 5, right? Making his max L 1 and his max R 2. We could have picked index 1, that would have been max L of 1 and max R of 1. So using the tiebreaker, we put him at index 5. If we were to get one more, we'd definitely put them at index 1. So this one is 3, 1, and 5. And I'm trying to find a way to like short circuit this without having to do it iteratively. Because I know iteratively should work for the first 2 cases, but once you get to that large case, we're going to have to start skipping steps. So I guess the real question is, I feel like we could break this up into like segments. So we know that after we put one guy in, this is broken into 2 chunks. But every guy that comes in, I mean, they'll alternate chunks, right? So one of them will be the larger of the 2 chunks, or they'll be equal. First guy goes in chunk A, second guy goes in chunk B. Now that pattern repeats, so we end up with this like a tree going on, right? So every, yeah, it should be a binary tree. But the trouble is that, interesting. So not every, the 2 children of the original tree, of the original node, the root node I suppose, they're not necessarily the same. So the max L and the max R are going to be different. And I feel like I'm, at this point, like, computing all of them, and I don't know if there is a relationship. Well, clearly there is a relationship between the mins and the maxes that I could probably, I mean, I feel like I'm at least in that scenario. Okay, huh, this gives me a clever idea. So here's what we do know, right? That in every scenario, this is my solid guess, in every scenario, we're going to alternate which child we go to. So we put one dude in the stall, right? So we have this big line of stalls, we put one guy right in the middle, so now virtually we have 2 lines of stalls, right? Left side and right side, right? And they're close to equal in size. The next guy that comes in is going to go to the left side, and the guy after that has to go to the right side. There's never going to be a case where left makes more sense. Is that true? I think that is true. That's my theory, right? And it does say in the rules that if there's a tie, we go to the left one. if there are still multiple tied stalls, they choose from the leftmost stall among those. So we're always going left, which is fantastic. So we're making this tree, right? But if we know what K is, like if we know what the last person in is going to be, we can only compute the ones we actually need. This is very exciting. This should give us a way to skip to that large data set without having to break anything. Yeah, so here's the thing, right? So, okay. Let me give an example. Can you see this tree in the middle? Let me see. I got a little lag on my screen cap, so let me pull up an open broadcaster. Okay, this tree, right? Oh, it's backwards. Okay, start the root. Left side, right side, whatever. Imagine that tree in your brain. Now, let's say that K is 1, 2, 3, 4, 5, 6. Oof, that's complicated. So basically, if I know what K is, I can know exactly where in the tree it should lie, and I can skip computation of any branches we're not going to do. Right? Because if I know how the tree builds, it's always a binary tree, so I know exactly how many are on each row. And I should be able to know, if I know how they fill in, and we compute the ones that we need to compute, which will save us a crap ton of time long term. So that's very exciting. So how does this tree fill up, right? So we have 1 right here. Now the thing is, I have to get this right. I have to be correct in how you build the tree. So if it's 8, right? So that's index 0, index 1, index 2, index 3, index 4, index 5, index 6, index 7, and there's, okay, now 4, 5, 6, 7, 8, and that guy is not here. Yeah, great. I'm good at counting, guys. Okay, so there's 4 and 4. So I'm gonna go to I'm gonna start. Yeah, so I'm gonna put Hugh in index 3, 0, 1, 2, 3. Okay, so I start at index 3. That's my total index. And then the next guy is actually going to go to the right first. Awkward. I can go to the right. Now he's physically to the right because I started on the left. That's fine. We'll make this work. Okay, and you're going to go to position 5, right? Which is that's 3, 4, 5. 2. That's 1, 2. Position 5. So I look right, and then I'm going to look left from 3, which is going to be position 1. Right? Now, if I were to put a 4th in, where would I put the 4th? The 4th guy, what's the rule for 4th? For each empty stall S, they compute L sub S and R sub S, which is the number of empty stalls S being the closest occupied stall on the left or right. Okay, so none of them right now are going to have a minimum better than 0. So if I'm min, farthest closest neighbor, that is for min, L sub. Okay. Yeah. Okay. So look for min L sub R, or min L sub S and R sub S. And then they look at max. Oh, okay. Right. Okay, yeah, that's great. So in this scenario, we're looking for the one with the furthest away neighbor. In that case, that's going to be position 7, which will be, yeah, 1 to the left. So position 7 is in the right chunk. Who knew? So that's 7. And then when we want to put in a 5th guy, our best bet. So everyone at that point is a sandwich between places. So that guy is going to be the leftmost. Okay, this is really awkward how we're building this. This is not following the pattern I anticipated. Because if I'm reading this right, the next guy in should go in position 0. Right? I think that's correct. And then that next guy would go in position 2. Right? I'm clearly building this tree wrong. And then this next dude would go in position 4. Now, so 0 by 5, 1, 2, 3. There's 4 right there. 5 is occupied. Did anyone ever occupy 6? 1, 2, 3, 4, 5, 6, 7. Fascinating. Okay. And then the next guy would come in at 6, which is the left side of this 4 node. Okay, so there probably is a pattern here. I just don't know what it is. This is trouble. Need another paper. Because if I can figure out how this tree is built, right, and then I know what K is, I can skip all the way down. It's got to be the way to do it. I just need a more predictable way to build this tree. Okay, so let's start simpler. It's a pity you can't see this paper. I'm wondering if I can crank this webcam so you can see it. I don't know how to read that or not, but okay, if I put my paper right there, maybe this will fly. Maybe. Yeah, let me crank these like this, right? What I want to do is, yeah, because the lighting is at least pretty consistent. Okay, I'm not drawing this upside down. You'll just have to follow me upside down. Oh my gosh, I could flip it. I don't want to, but I could. Yeah, that's fine. Okay, we're here. Okay. Let's do the 7 case really quick. OBS. So, if we have 7 to start, right? 1, 2, 3, 4, 5, 6. Okay, this is n equals 7. Right, we'll just do it as many k's as we can get. So the first guy comes in, and he goes definitely to position 3. I'm trying to write these up really quick. 5, 6. That guy goes into position 4. Right, that was k equals 1. He goes in 4. Okay. Now, next dude comes in. Sorry, this is way bouncy. I apologize about that. You should have a deal. Just gonna make this bigger. Why don't I do that really quick? Okay, that'll help. And then really quick with props. Can I flip this? There is a way to flip it. Flip image vertical and horizontal. Cool. Cool. Alright, that's a little better actually for you. So yeah, you're actually following what I'm writing now. Wow, nifty. I'll get this set up well later, but for now, you're actually following. So cool. Okay. So when n is 7, we go to 4. Okay, that was 1. And then the next guy in is going to go to 2. Alright? So when they're balanced, we have 2 that come up of size 3. So the next guy in is going to go to index 2. So when k equals 2, we go left. And the next game, we obviously go to 6. So then we go to 6. And that's k equals 3. Now, the next guy, at this point, everybody is equal, right? Every chunk is chill. Every chunk is good. So we will, at that point, go just from left to right. That's 1, 3, left, right, and then we'll go left, right, right? That'll be 5, that'll be 7, right? 1, 3, 5, 7. Okay. So in a balanced, it's just left to right. Left to right is how we're filling it. but we don't always have a balanced tree. So what if n equals 6? Right, let's just try that really quick. So we go 1, 2, 3, 4, 5. Okay. So just write these in 1, 2, 3, 4, 5, and 6. Okay, so the first guy comes in, and he can either go to the left or to the right, but we're going to put him right here. So k equals 1. Our root node goes to 3. Okay. Now we're going to go right first. So basically we have two nodes are created. The left node is little. It has basically 2 contiguous spots. And the right one has 3. So if it's unbalanced, the right one will become larger. Well, here, right, in the sunspot there. That's awkward. Because we picked the left one in a balanced scenario. So that means that the next one will come onto the right. Okay, and that's going to go into position 5. So k equals 2 goes to position 5. Now that spawns a 1 and a 1, right? Well, size of 1 there. Which means that the next one in goes to 1 in that case, actually. So it'll go to 1. K equals 3. So on this side, we actually get a 0. You don't have any room there. And on that side, we have a 1. So now we have a 1, 1, 1 scenario. So we will fill from left to right. So k equals 4. Gets 2. K equals 5 gets a 4. And k equals 6 gets to be 6. And there we are. Okay, so, sorry you can't read that super well. So what does that teach us? So if it's unbalanced, if it's imba, right, we go right first. Right first. If it's balanced, we go left first. But, that being said, we have edges to consider, which, we're going to run into these edges over here, where we can't go left anymore. Now that's only going to happen on the last level, though, isn't it? Like, yeah. Yeah, that's only going to happen as we're getting to the very end. This is true. So we will have a full tree, and it'll be a balanced tree, until we get to the last level. And then once we're at the last level, we'll have to figure out where we lie. I think this is the right way to solve this problem, but I'm not 100% sure how feasible this is. This is a fun problem, actually. This is really fun. Because I do think it's going to be a tree, and I do think we can short circuit huge portions of the tree. But it's going to be hard to... it's hard to know exactly where in that tree we're going to lie. Especially without computing each level, right? So there's got to be a pattern, right? So if k ends up balanced, okay, so we have two options here, right? There's really only two kinds of nodes, right? There's a node that's even, and there's a node that's odd, right?
That's right. We waste time on
and
we take the fort.
If it is even, then it's going to go right first with the... Yeah, if it's even, it goes right first. And by even, I mean if the number Yeah. Okay. Okay. So if the number of contiguous stalls is even, then we go right first, then left. Having 6 is a bad example because it immediately runs into a wall. So if we look at 7 and 8, right? So 8 was even. Gosh dang, I'm gonna do this again. 1, 2, 3, 4, 5, 6, 7. Sure. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. So if the S is even, meaning the number of contiguous stalls is even, right? We end up in the left side of it. So we go to position 3, and that gives us 2 options. That gives us one of size 4 and one of size 3. So then we'll go right first. So even is right first. So that place we'll put it at 6, I think. But to be aware, there's 1, 2, 3, 4. Okay. So it's even. We will go right, and it will have S over 2 spots left. Okay? And so R will go there, and then L, you'll get S over 2 minus 1 spots left. Right? And who goes first in that scenario? Right will go first, of course. So right goes first, and it's actually even. So we will do that same thing again. We will go right, which is gonna turn into S over 2 spots left.
I guess you're the only one not busy.
1. And that's good. So there are 2 spots left, right? We go right. And there's well,
pretty big difference. So
put that at 8
How
in
is it
that
now?
scenario.
that would be proposal for both fonts here. So
And there will in fact be only 1 spot left.
it's better. It doesn't look
It's
great
neat.
still.
When I said spots left, I mean the total contiguous blocks that are remaining when we're done with this, which is exciting. And then we'll go to the left, which will be 0.
But this
That's
one is
nifty.
pretty skinny as
It's very
well.
nifty.
If I do
But here's the thing. So we'll go right, left.
I guess something like this.
Now in generation 2, we will go right,
Right now, this comes with both.
and then we will go all the way from the left. So we'll go left, 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 left.
Alright.
So it's the generation 3 that we're worried about, right? Because generation 1 is simple. 2 works, but how do we start picking in that last generation? So I guess the only real way, let's take a look at something larger. What if we went up to like,
Okay, I think it's good now. Okay, it's still kind of skinny and wonky, but if I had some more
we'll go up to
sweeping,
16.
get rid of bigger.
Just do it real quick.
Yeah. Headers are bigger and
Now,
get skinnier.
the thing about 16 is that it's just 2
It
8s.
used to be able,
Right.
also it used to be able to
3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
drag them around.
I haven't really decoded yet, by the way.
I'm gonna put like it as part of this. So you can,
Yeah, so there's
yeah.
16
'Cause it's
holes,
sometimes you
right?
want to configure something based
And that's actually even as well, which is not ideal, but we're trying to figure out the even case. And we're trying to find some sort of pattern between evens and odds such that, how long have I been streaming? I'm almost out. Gosh dang, that's too bad, it's gone fast. We're trying to find a pattern so that we know how to build a tree so that we can short circuit all of the tree madness and not have to do this iteratively. So when S is even, our first one is going to go into 8, which is the leftmost middle spot. So that's position 1. So that's 8. Now, since S is even, we will go right first, followed by left. And this should have 8 left, right? 1, 2, 3, 4, 5, 6, 7. Wait. Yeah, so that does have S over 2 total. And I'm going to put that guy right there. So I will have 3 to my left and 4 to my right. So he goes to 12. Okay, so if I know how much I'm going to have, right, which is S over 2 in that scenario, I'm going to break that into S over 2 minus 1 to my left and S over 2 to my right, because I will be consuming a spot. So I know that if S is even, that's what's going to happen. I'm going to go, that's how it breaks down. And then over here, I'm left, instead of with 8, I'm left with 7, right? Which is, you know, S over 2 minus 1. So if S is odd, I get S over 2 minus 1 on both sides. Sorry, not S over 2 minus 1. S plus 1 over 2 minus 1, right? So I get 3 on both sides. When I split it up, right? Okay. So I know how this goes. So what am I going to get over here? So he's in position 12. So this guy is going to get S over 2 on the right and S over 2 minus 1 on the left. That's correct. Okay. At that point, I'm going to take that 4 first, because that is the largest one, right? And then all of those 3s are going to go from left to right. Does the pattern follow? Okay, so I'm going to go to 4, and that's going to give me a 2 here and a 1 there. And then I'll go 3, and it'll be a 1, 1. 3, 1, 1. It's a 1, 1. Right? And then I'll take the right one, the furthest right, and then left. I think that's how you build a tree. You take the furthest right one, and then all of the lefts. And if you build your tree like that, I think it will always work. Take the furthest right node, like literally the furthest right node, and then use all the lefts. I think that's how it got built. Okay, so build tree. Build tree. Furthest right node. Right node. And then from left to right. And for what it's worth, that furthest right node will always have the biggest option. It'll either be equal or have the same size as everyone else. And it doesn't matter in that case. That's fun. So furthest right nodes, right child. And then you go left. Right? So 8 is the furthest right node. So we go right, and then we do a left. Given generation 2 right here, we do the right child here, right? And then, okay, so I'm going to put someone at 12, right? Put one at, where'd you go? You went what, 4? 1, that's 2, that's 3. Okay, so node 1, node 2, node 3. When it comes to node 4, you've got an option of a 3, a 3, a 3, or a 4. So you go to the 4, which is 13, 14, 15, 16. You're going to split that in 2, so you're going to end up at 14. And then you'll proceed left child, right child, left child, right child. Okay, so for each generation. So for each generation. Left child, right child, left child, right child. Okay, so when we're making children, making children, right? Rightmost node has its right baby. Has right baby. Then every node, starting at left, has, I guess it doesn't matter if they have the right baby or the left baby. Is it even or odd? Right, so this 7, it's an odd, it spawns left or right. Now the right one doesn't matter in that scenario, because they're all actually going to end up equal in that world. So odd is nice. Once you get to odd, things start to like really work out, don't they? It's these even ones that have like a right kicker. Right, nobody likes those even ones. Because you create 8, and you have a whole of 4 right there, right? So 1, 2, 3, 4. So you're actually going to do it again. So as long as there's a... Here's the thing, though. I think everything's going to be even except for that farthest right side. So you go left. And then there's a space. We can take a 3 in there. You could take a 3 there, or you could take a... Yeah, the 4's already taken. So... the left, then right, then right. Cool. Okay, so that's where I'm gonna have to stop for now. But I do think that I can code that up, and so we can say that, oh, the starting n is like 100, and k is 18. So I can say, well, okay, what generation is this going to be on? And I'll say, okay, what is 10? Log base 2 of 10, right? Log base 2 of 100. And I'll say, okay, that's 2, 4, 8, 16, 32, 64, 128, right? So we're somewhere between 6 and 7. So we will be into the 7th generation. 7th gen. Into the 7th generation. And so we'll say, okay, what's 100 minus 64? And the answer there is, oh, I don't know, 36, maybe? Yeah, 36. So we'll say, okay, the 7th generation has to have 36 people in it. Where will those 36 people lie? We will say, well, it's definitely not on the furthest right side. Yeah, it's interesting. Okay, I can figure this out. So, I've learned how the tree gets built. I did not write any code, but I bounced this image up around a lot. Yeah, I think it's a good place to stop for today. I'm gonna check chat really quick. Didn't see anybody chatting, but I don't know that anybody can chat right now. So we're going to go ahead and end it right there. I'm going to play some PUBG to finish out my lunch. Let me know if you have any questions in the comments on YouTube, or shoot me an email. Alright, thanks everybody. Have a good day. We figured out how the stream gets built, or the tree gets built, and I think that's going to allow this to work. Alright, thanks. Bye.